Welcome to our webinar dedicated to the CPU-based threading models application in Python for HPC computing. The webinar is intended for developers, researchers, and HPC practitioners who require assistance in the implementation of parallel computing solutions in Python applications. A few notes prior to commencing. The Synthesia.io platform is used to pre-record and narrate the webinar, allowing for the brief presentation of various subjects and methods in the condensed amount of time allotted. After the webinar is over, anyone with the link will be able to download the recorded and narrated video file. We will also give the attendees a URL to a Git repository containing all the code and documentation associated with the webinar's topic, so they can delve deeper into the subjects at any time. While it is not mandatory, we would expect that you, as a participant, can write modify Python code using a text editor or an interactive IDE. Have basic knowledge what are threads and how they are implemented in Python. Have a basic knowledge in multi-threading libraries, ideally OpenMP, and how they work. Know what is hyperthreading and simultaneous multi-threading, SMT. Know what CPU cores and CPU threads are and how to control their utilization. Have basic experience with Slurm on EuroHPC or other HPC clusters. Our webinar is structured in the following way. We start with a short introduction, followed by an overview of the CPython direct interaction with multi-threading libraries. Next, we explain how to run Python code as multi-threaded using just-in-time JIT compilation. Afterwards, we show how to disable Git and use Python interpreter itself as multi-threaded application. We also provide an important discussion about how to handle data in Python to facilitate multi-threading executions. Lastly, we go over the fundamentals of writing Slurm job scripts that enable Python multi-threading applications to run properly. Let us start with some general features of Python. Python excels at workflow orchestration, importing data, passing to modules, receiving output, storing results. Data management, NumPy arrays, data structures, file I/O, pre-processing. Simple code blocks, connecting external execution modules together. Python is not efficient for complex and heavy computational subroutines, heavy computation that requires threading, loops over large datasets due to object-based memory model. Building or using fast loop solvers is one of the hardest parts of any Python computational code project. While there are some intrinsic components that support the loop solving, Python in general is not good in that. However, when working on scientific projects, it becomes difficult to avoid solving enormous loops, especially if they involve operations with floating point data. Whether it is matrix multiplications, numerical integrations, or iterative solvers, these loop-based computations are where the majority of CPU time is spent. In general, the Python loop solvers are not effective, primarily for two reasons. First, Python uses objects, not arrays of data, to iterate over. When you iterate over a Python list or other container, you're iterating over references to objects, each with its own memory allocation, type information, and overhead. This object-based memory model prevents efficient cache utilization and creates significant overhead compared to iterating over contiguous arrays of raw data. Second, the loop solver constructions themselves are problematic. Python's for loops operate at the bytecode level, where each iteration involves multiple bytecode instructions, object lookups, and method dispatches. This interpreter overhead accumulates rapidly in nested loops, making Python loops orders of magnitude slower than equivalent compiled code that operates directly on memory. It is self-evident that in order to solve the loop problem in Python, we must either refrain from solving the loops in a Pythonic manner or allow Python to natively parallelize the existing loop solver blocks using multiple threads. During this webinar, we will try to explore both ways. Finding a solution to the loop solving issue that supports a massive data processing in Python should be based on the following presumptions. The modern Python is CPython, and that means it can execute externally compiled binary code, passing the data to that code in the appropriate data format, not as objects. We can use externally compiled loop solvers that handle the loops through a pre-compiled C, C++, or Fortran code linked to multi-threading libraries, like OpenMP, TBB, or pthreads. It is possible to disable the global interpreter lock, GIL, and turn the Python interpreter into a multi-threading application. The parallelization of the loop solving in Python can be handled in 3 different ways. 1. The data is provided by the Python code, but the solver code is a component of external binary code that has been compiled and uses multi-threading libraries to process the threads. 2. The loop solver code is implemented and provided by the Python code. However, it is executed by external multi-threading libraries after it is compiled in memory using a just-in-time compiler, JIT. 3. The Python code implements the loop solver code and provides the data. However, the loop solver code is executed by internally controlled Python threads that run in parallel after it is compiled in memory using a just-in-time compiler. If we want to implement method 1, then we need to write the loop solver code in C, C++, or Fortran, adding to it an additional code that allows the use of a selected external multi-threading library. In that case, the worker threads bypasses GIL. Afterwards, we have to compile and link that code to produce a shared library, a .so file that can be executed from within the Python code utilizing ctypes module. In case we want to follow method 2, then we need to use a special Python framework like Numba or PyOMP. This type of framework decorates or slightly modifies the native Python code, making the loops there solvable by a selected and external multi-threading library. Again, the worker threads bypass GIL. Method 3 turns Python interpreter into a free-threaded application that can compile LLVM intermediate representation, IR text, and execute it based on native Python threads. That method is very innovative and can be explored to create CPU arch-independent parallel loop solvers. The most important step here is to prepare the data for passing to the external compiled code. Be aware that we are unable to pass Python objects straight to that kind of executable code. The binary code can only accept scalar data or data arrays that are stored in memory and have the types recognized by the corresponding programming languages. All data type conversions need to be performed in accordance with Foreign Function Interface, FFI, a protocol for a programming language to call functions written in a different language, typically at runtime. So we can use here either ctypes module or an interplay between NumPy with ctypes. Here is an example that shows how to use ctypes type conversion. We illustrate the process of converting a list of data into a C array with double floating point precision. Another example shows the aforementioned interplay between NumPy and ctypes modules. Keep in mind that NumPy is only useful in this situation if we wish to pre-process arrays, such as changing the values or reshaping them before passing them to the external code. In all other circumstances, the use of NumPy is not mandatory. And here is a table that shows the Python to C data type conversion rules used by ctypes with examples. And here comes the code execution workflow. The Python code organizes the data, converts the data types using ctypes module. Then it calls ctypes.cdll to pass the data to the external code that already exists in the form of shared library. That happens through the data buffer, where the array formatted by the ctypes module is kept. Note that CDLL is a class in Python's ctypes module that create an object connected to a dynamically loaded shared library, .so on Linux, for utilization. Also note that CDLL needs to call the DL open system function provided by the Linux OS to dynamically load the shared library into a process's memory. Additionally, CDLL reads the names of the subroutines, voids, within the shared library in a manner that allows the Python code to select the subroutine to execute by providing its name. During the execution of the selected code, if that code was linked to a multi-threading library, that library creates and controls the execution of worker threads on Python's behalf. This implies that those threads are bypassing the GIL, resulting in running a multi-threading parallel process. That way, the running Python code only gets the outcome of the parallel execution once it is finished. The same applies to the case when NumPy is employed a helper to facilitate the data conversion process. The application of NumPy does not change the execution workflow of the external code. It is important to note that the data buffer has the same size and structure whether NumPy is used or not in the Python code. As previously mentioned, NumPy only assists with managing arrays in Python code prior to the data being stored in the data buffer for external code access. Here is an example of an externally organized solver in C that relies on the OpenMP library for parallelizing the loop solving by using multiple CPU threads. So it is an isolated procedure code that may call other functions and procedures. Our advice is to use here C or C++ code because of the perfect match the compiled code has with C types module in Python. In case you need to use Fortran code as an external loop solver, the best way to organize the code is to add the subroutine with the loops within the contains part of a Fortran module. You need to use ISO C binding module to provide data type interoperability with C, and adopt bind interface to define the C name of the subroutine. That way, the produced compiled code can be executed from within the Python code using C types module. In our examples, we will show how to rely on the following external multi-threading libraries: OpenMP, POSIX threads, also known as P threads, and threading building blocks, TBB. To be able to compile and run the example code we provide, you need to have a Linux desktop system running on a processor with at least 4 CPU cores and have the hyperthreading activated for those cores. The QR code provides an easy way to get the URL. Use Git to clone the repository locally on your Linux desktop system. Keep in mind that the repository also has all the developer information you need, including instructions on how to install the necessary libraries and run the examples while keeping an eye on the parallel execution metrics. Here is a display of the file subtree in our webinar repository where the files you needed are located. Each subfolder contains a code related to the use of different multi-threading library: OpenMP, pthreads, and TBB. The developer documentation is the most important one here, for it provides a comprehensive explanation about the code. For each library, there is a programming code that must be compiled before running the example code. Each folder also contains an example Python code that should be run only after the corresponding code is properly compiled, following the documentation. And finally, there are files contains the metrics collected during the execution of the example code. The following metrics show the parallel execution of a loop solver written in Fortran 2003, compiled with gfortran and linked against OpenMP library. The data shown has a very specific pattern. There is one main Python thread with high CPU load, waiting for workers to complete and controlling the execution of 7 internal threads. Those are global interpreted lock threads, serially executed, no parallel execution there, and 4 parallel worker threads created by the external pthreads library actively computing. Thus, our Python application must run and maintain 12 running threads in total for the 4 requested OpenMP threads worker threads. Be aware that the CPU percentages shown by PSELF are averaged over the entire process lifetime on a per-thread basis, not on a per-process, and they do not represent instantaneous values. This is why, when using the tooltop, you might see 400% total CPU usage for this example instead of 500%. Take this into account for organizing the resource accounting. For instance, If you want to run this job on a Slurm-controlled cluster, the CPUs per task must be set to 4, not to 12. Almost the same is the situation with the use of POSIX threads library. Here we show the metrics collected during the execution of loopsolver written in C++, compiled and linked against pthread library. Again, here is one main Python thread waiting for workers to complete. It controls the execution of remaining 7 internal Python threads. Those are global interpreted lock threads, and they are serially executed. The pthreads library runs and controls in parallel 4 worker threads, actively computing. Thus, our Python application must run and maintain 12 running threads in total for the 4 requested pthreads worker threads. Here, also be aware that the CPU percentages shown by PS, ELF are averaged over the entire process lifetime on a per-thread basis, not on a per-process, and they do not represent instantaneous values. This is why, when using the tool top, you might see Jotram 400% total CPU usage for this example instead of 500%. Take this metrics patterns into account when planning to establish a resource accounting on the processes running. The TBB metrics show a slightly different pattern. The metrics shown here are collected during the parallel execution of a loop solver written in C++ and linked against TBB library. The number of requested TBB threads is 4. 3 TBB managed threads are fully loaded. The 4th loaded thread is the main Python thread. It participates in parallel work via work stealing. So you may see fewer dedicated TBB worker threads than requested, but the total active threads match the requested number. This is the expected TBB behavior. The Python's internal threads, GIL threads, background threads, do not contribute to the total load, but if they need more CPU time, that will reduce the ability of the main Python thread to fully utilize itself. In conclusion, the direct execution of compiled loop solvers linked to multi-threading libraries through the ctypes module is a straightforward yet highly effective method for parallelizing the solution of massive loops. Of course, this method necessitates proficiency in programming languages such as C, C++, and Fortran, which occasionally complicates projects that employ this approach. However, if Python code is required to develop loop solvers, this approach is rendered obsolete. And if that is the case, you might employ a Python framework that uses external multi-threading libraries to parallel execute the Python loop solvers code that is compiled in advance into bytecode in memory. This is how we are coming to the next method, the use of external multi-threading libraries based on Python code byte compiled in memory by just-in-time compiler. Here, we will show how to employ 2 highly valuable Python platforms for parallel execution of Python code, Numba and PyOMP. Just keep in mind that PyOMP is a Python product built on top of Numba. Before digging deep into Numba and PyOMP, we need to introduce the just-in-time compiler, known as JIT, for it is the tool both Numba and PyOMP use to compile that Python code that later will be executed with the help of parallel threads. So what is JIT? JIT is a technique that combines the flexibility of interpreted languages with the performance of compiled languages. Instead of compiling code before execution, ahead-of-time compilation, or interpreting it line by line at runtime, pure interpretation, JIT compilation translates code to machine instructions during program execution, right when it's needed. Note that JIT is based on llmv.org project code. How JIT compilation works? First, we need initial execution, interpretation. The function is first executed using the standard Python interpreter. The JIT compiler profiles the code to understand which code paths are executed most frequently, hotspots. What types of data are being used? How many times loops iterate? Second, we are going through the compilation phase just in time. When a function is called frequently enough, the JIT compiler triggers compilation. The Python bytecode is analyzed and translated into an intermediate representation, IR. The IR is optimized, constant folding, loop unrolling, dead code elimination. The optimized IR is then compiled to machine code, native CPU instructions. Third, we proceed with the execution of the compiled code. Subsequent calls to the function use the compiled machine code instead of bytecode. The compiled code runs at near native speed, comparable to C, C++, and Fortran. Type information is baked into the compiled code, eliminating runtime type checks. Fourth, we employ an adaptive optimization. The JIT compiler may recompile the function if execution patterns change. For example, if a function that was optimized for integers starts receiving floats, it may be recompiled with different optimizations. Number provides automatic parallelization through the ngit Python code decorator and prange function. It replaces the classic range function. Parallel execution is achieved by distributing loop iterations across multiple threads. The most important number features are thread creation. Number worker threads are created by the threading backend, TBB, OpenMP, or WorkQueue, when marked parallel regions are encountered. GIL independent multithreading. GIL is released in JIT compiled code, enabling true parallel execution. Thread count control. The number of threads is controlled by the number_num_threads environment variable or programmatically via set_num_threads. Multiple threading backends. Number supports multiple threading backends, TBB, OpenMP, WorkQueue, that can be selected via the environment variable number_threading_layer. It is very important to know which Python code can be effectively parallelized by Number and which one cannot be run in parallel. Number can parallelize numerical computations on typed arrays, not Python lists of objects. In Python code that uses Number, the parallel region decorated by ngit must use the prange function instead of range for parallel loops. Plus, that loop solver needs to work with NumPy arrays instead of Python lists. It is because the Python lists are composed of Python objects, whereas NumPy arrays are C arrays that are typed. Along with the code compiled by JIT, the C arrays can be transmitted to the multi-threading library as is. Number can handle the following data types for the typed arrays: 32-bit integer and float, 64-bit integer, float, and complex, and 128-bit complex type. NumPy math functions are supported in the parallel regions, for they can be easily compiled by JIT into executable code. That applies for the basic arithmetic operations, the comparisons and bitwise operations. Number parallel regions can handle parallel reductions with proper synchronization. Natively supported reductions are sum, product, minimum, and maximum functions. Number can also handle custom reductions, as long as the reduction operation is simple and operates on numerical values. Here we show 3 cases of custom reduction that can be handled by Number: sum of squares, weighted sum, and maximum absolute value. Number automatically makes reductions thread-safe for simple operations. The reduction variable must be initialized before the loop, as it's shown here. In addition, one must use simple numerical operations and avoid complex logic that might prevent automatic reduction detection. For very complex reductions, consider using separate arrays per thread and combining results sequentially. Simple conditional logic is also supported by Number if declared in the parallel regions. Of course, Number can handle nested loops, but you need to make sure that the external multi-threading libraries can effectively manage the employed level of nesting. PyOMP, or OpenMP for Python, is an extension to Number that provides OpenMP abstractions for CPU parallel programming in Python. PyOMP provides OpenMP-style parallel programming using the unjit decorator from number.openmp and openmp_context. Parallel execution is achieved using OpenMP directives like parallel for within with OpenMP-based contexts. Thread creation. OpenMP worker threads are created when parallel regions are encountered. PyOMP's parallelism is independent of Python's GIL. GIL is released in JIT compiled code, enabling true parallel execution. Thread count control. The number of threads is controlled by the OMP_NUM_threads environment variable. OpenMP backend. PyOMP uses OpenMP runtime libraries, typically provided by the system compiler or LLVM. Let's start with a basic example. Here is a simple code that employs OpenMP extension installed on top of Number, which is precisely what PyOMP is. Note that we do not need to provide parallel switch to the ngit decorator, for it is always presumed. Note that unlike pure Number, the OpenMP extension does not employ prange function. It relies on the classic range. Since PyOMP relies on the OpenMP context to implement the reduction, that simplifies the process compared to the declaring a reduction in terms of native Number parallel code. Now let us run the example code, collect the metrics, and analyze them. The webinar code and documentation repository's URL and instructions for cloning the content are provided below in the event that you have not yet downloaded it. The displayed file tree show the location and names of the example code, developer documentation, and example metrics collected during the execution of the example code. The metrics presented here illustrate the current CPU load due to the running threads for running Number and PyOMP code. Yellow members are for threads that are created and kept up to date by the external threading model library, in this case OpenMP. It is evident that those threads scale well as they run in parallel. In comparison to the PyOMP, the Number execution performer is a little slower. That was intentionally generated by executing an additional process on the same system that reduces the load exclusively on specific CPU cores to verify the bindings. This demonstrates that the only threads that compete for the loaded CPU threads are suppressed, as they must share the same hardware threads with other executions, which is not indicated in this instance. The internal threads of Python and the threads that are colored in gray. They are both idle and executed serially, which results in a zero CPU load on the system. The PS output shows clearly the Python internal threads, colored gray. They are in idle state most of the time. Those are GIL threads, the numbers colored in yellow and related to the worker threads created and controlled by the employed external multi-threading library, which in this case is OpenMP. They actively utilize the CPU cores. These low numbers are the averages of values collected over a time window. That is why they do not seem to have anything to do with the results reported by the top tool. Do not rely on those values to measure the current CPU load or for scaling measures. When the tool PS is run for the PyOMP execution, those lines are shown. The pattern and thread list they display are essentially the same as those seen in the Number example run. Here we have high CPU utilization occasionally. The numbers depend on how long it was between starting the PyOMP calculations and calling the PS tool. Here we show how to use Conda and install both the TBB libraries and TBB headers. The latter requires the installation of TBB Devil package. Those are requires by Number to enable the use of TBB multi-threading library in the example code we provided in the webinar repository. This section is intended for more experienced Python programmers and users. By including this content in the webinar, we hope to pique your interest in native support for Python multi-threading. Although this Python parallelization technique could be considered experimental, it is an impressive example of the exceptional CPython's capabilities. Before starting with the details, we need to be sure you can differentiate between multi-threading and multiprocessing, for those are two different things in Python regarding the presence of the global interpreter lock, or GIL. Multiprocessing creates separate processes, each with its own memory space and its own GIL. Multithreading creates threads within a single process, sharing the same memory space and competing for the same GIL. Threads can directly access shared variables. Processes cannot. They must use queues, pipes, or shared memory objects. Multiprocessing bypasses the GIL by using separate processes, not by enabling multi-threading, while the multi-threading needs GIL to be disabled. We will begin by giving a full explanation of how and why to make a Python interpreter that can naturally handle multiple threads in parallel. Subsequently, we will elaborate on the functions of the two most critical modules that are essential for the productive execution of multi-threading in Python. Lastly, we will set up a work environment where we can run the example code we made for you and examine how it handles the multi-threading parallelism. Originally, Python interpreter cannot run as multi-threaded application. What prevents Python from running as a multi-threaded application is its global interpreter lock, GIL. The GIL is a mutex, a mutual exclusion lock, implemented in the code of the Python's interpreter. This impacts the management of Python threads during the execution of the code. Thanks to GIL, only one thread can execute Python bytecode at any given time. With GIL enabled, a thread must acquire the GIL before executing Python. A thread must acquire the GIL before executing Python code. Multiple threads compete for the GIL when it becomes available. The GIL is released after a certain number of bytecode instructions. Therefore, it is GIL who prevents the implementation of shared memory parallelism through multi-threading in Python code. Before providing an explanation about how to disable GIL, let us provide a schematic explanation about how the threads compete for GIL when it is enabled. As shown in this execution diagram, the GIL ensures that even if you create multiple threads in Python, only one thread can actually execute Python code at once. The diagram illustrates the execution flow over time. Initially, all threads start in a waiting state, competing for the GIL. When thread 1 acquires the GIL, it transitions from waiting to executing Python bytecode. During this time, threads 2 and 3 remain in the waiting state. They cannot execute Python code because they do not have the GIL. After thread 1 executes a certain number of bytecode instructions, it releases the GIL. At this point, all waiting threads compete for the GIL. In the diagram, thread 2 successfully acquires it and begins executing, while thread 3 continues waiting. This process repeats. Only one thread executes at a time, while others wait. This design was chosen to simplify Python's memory management and make the interpreter thread-safe. However, it has a critical consequence. Python code cannot achieve shared memory parallelism through multi-threading, even on multi-core systems. The diagram clearly shows that while one thread executes, the others are idle, wasting available CPU cores. This is why all multi-threading execution must be handled using external components, libraries or compiled code that operate outside of Python's interpreter and are not bound by the GIL. To make Python interpreter running multiple threads in parallel, we need to disable GIL and thus turn the Python interpreter into a free threading application. That is something we need to specify during the compilation of the Python interpreter source code. In the latest versions of Python source code distribution, the configure script supports the compilation configuration option that completely disables GIL. Note that working with no GIL Python, where GIL is disabled, requires excellent understanding of what happens with the Python bytecode execution once GIL is switched off. That is to say, state-of-the-art coding is needed for any multi-threading Python execution where the parallelization is based on the parallel execution of Python threads. Here we are not talking about running external threads controlled by an external compiled code, which is a completely different matter and has nothing to do with running Python threads in parallel. No GIL Python is useful to handle the following cases. CPU-bound Python code that can be parallelized. That implies running in parallel a Python code that implements numerical computations, image processing, and data transformations. Embarrassingly parallel workloads where threads work on independent data. Performance-critical applications where the GIL is a bottleneck. Code that already uses proper synchronization and thread-safe patterns. Avoid no GIL Python in the following cases. Handling I/O-bound workloads. In that case, better rely on async I/O module or standard threading, for GIL is released during I/O operations. Code with extensive shared mutable state. If that is the case, consider the use of multiprocessing module. using C extensions that are not thread-safe. Simple scripts, whereupon introducing no GIL code complexity may not be worth it. Code that relies on GIL-protected assumptions because it may require significant refactoring. Since the C extensions are important, here are examples of potentially thread-unsafe C extensions that must be avoided when utilizing no-GIL Python interpreter. Older versions of Pillow, some image processing operations in older versions use global state or were not designed for concurrent access. Custom C extensions with global state. Here we include any C extension that uses global variables, static variables, or maintains internal state without proper synchronization. Extensions using non-thread safe C libraries. Those are C extensions that wrap C libraries that are not thread safe, like some older numerical libraries. Extensions not tested with no GIL Python. Even if an extension appears thread safe, it may have subtle issues that only appear when the GIL is disabled, so proper testing is required. We are now coming to the most interesting part, using LLVM intermediate representation, IR and internal threading control in Python. That way, we can execute C code through the Python interpreter in multiple threads. The threading module is native to the Python code, and it provides the interface for creating and managing Python threads. Its role is to create multiple worker threads, whereupon each thread executes the same Python code independently. To control the thread execution, in which case each thread performs CPU-intensive Python work, and to handle the thread synchronization to coordinate thread startup and completion. This module behaves differently depending on the presence or absence of GIL. With GIL-enabled Python, only one thread executes Python code at a time, which implies serial execution. With no GIL Python, multiple threads execute Python code simultaneously, and that is parallel execution. The LLVM-Lite module is external to the Python project code. It provides Python bindings to LLVM, enabling JIT, just-in-time compilation. In particular, it passes LLVM intermediate representation text into an in-memory module as pure Python code. It does IR verification by validating the IR module structure, performs MCJIT compilation during which it compiles IR to native machine code, implements function address retrieval by getting the address of the compiled function, and it controls the per-thread usage. That means each thread independently uses LVM-Lite to pass and compile the cached IR text. The term MCJIT may be confusing, as we had previously discussed JIT during the presentation of Number. It is important to note that the MCJIT component is a part of the LLVM.org project's code and is not a component of Number. MCJIT stands for Machine Code Just-in-Time Compiler. In our webinar repository, we offer a thorough comparison of the Number-adopted JIT and the JITs that are available in the LLVM.org code. The LVM-Lite module is very specific to the Clang compiler version used to produce the LLVM intermediate representation, IR text. These are the causes of this level of specificity. LVM-Lite is a Python binding for a specific LVM version of the LVM.org code. Clang is the C compiler frontend that generates LLVM IR, and it is part of the LLVM.org code. The LLVM IR format can change between LLVM.org versions. If Clang generates IR using features or syntax from a different LLVM version than what LVM-Lite supports, parsing will fail. Therefore, UU must use a Clang version that matches LVM-Lite's LLVM version to ensure IR format compatibility. Unlike typical multi-threading examples that show compiled code parallelism, supported by external compiled threading libraries, here we focus on Python code itself, running internally manageable threads in Pythonic way. Therefore, what we are going to show next does not rely on external threading libraries like OpenMP, TBB, and pthreads. Our goal is to load C code in Python, translate that code into the intermediate representation instructions supported by LLVM through LLVM-Lite module, and execute that code using native Python threads. For that purpose, Python itself handles 3 types of threads, each with its own role. The execution of n number of worker threads requires another n threads to support the worker ones. The first type of thread is the main thread. This is the primary Python interpreter thread. It executes the main Python code, creates and manages worker threads, and waits for worker threads to complete. When its load is examined, it shows 0% or very low CPU usage because it spends most of its time waiting. Next come the internal Python interpreter threads, and their number is n-1. They are created automatically by the Python interpreter for different auxiliary purposes. Garbage collector thread that manages memory cleanup, threading module internal threads to manage thread lifecycle and synchronization, signal handling threads to handle system signals, and I/O threads that handle asynchronous I/O operations if such operations are demanded. Most of the time, all those types of threads show 0% CPU usage because they are idle or perform minimal work during CPU-bound execution. And finally, come the worker threads. Their number is n, and chronologically, they are created after the other types of threads. Those are the threads that actually execute the parallel code and create the high load on CPUs. This sketch shows how the native Python threading works in our case if we can use no-GIL Python. The startup part is performed in a serial manner by the main thread. First, it translates the C code into LLVM intermediate representation text and caches the result in the memory. Afterwards, it starts 2 times n threads, where n is a number provided by the user who is starting the script. Upon completion of the parallel execution part, the remaining code in the script is handled again by the main thread and executed as a serial code. In order to execute the example code and check the results, we need to set up our work environment. That requires the installation of free threading, no-GIL, Python, Miniconda 3, LLVM Lite Python module, and Clang compiler. And in case you have not done that yet, clone locally the webinar repository containing the example code, documentation, and other useful information. Finally, run the example code and collect and examine the metrics. Before running the examples and collect the metrics for analyze, we remind you the location of our webinar repository. You should clone the webinar repository locally on your desktop system if you want to run the examples or read the documentation. The displayed file tree show the location and names of the example code. Developer documentation and example metrics collected during the execution of the example code. In the same folder is the external C code and some homework for you. The easiest way to create your own installation of no-GIL Python is to download the latest Python code and compile it by yourself locally, passing Disable GIL option to the configure script. That way, you will be able to work with the code example we provide you with later. Here we show how to install Miniconda 3 to bring Conda tool into your system. In case you have Conda already installed, you may skip this step. The last installation step is to bring locally the LLVM Lite Python module together with compatible Clang compiler version. That is required for the translation of C code into LLVM intermediate representation text. Here, Clang will not be used for compiling binary code. Currently, the latest LLVM Lite module needs a compatible Clang, which is why we provided the version number. Running the example code is simple. Set the necessary environment variables, enter the directory where the code is located, and then execute the script. Note that the code execution will take long enough to allow you to collect the metrics related to the code execution in another terminal window. Remember, the code comes with a comprehensive developer documentation located in the same folder. Collecting the metrics of the code execution is simple. The following useful commands will show you the load the parallel Python script create on the logical processors. In a moment, we will discuss the meaning of the numbers displayed. Be sure you execute those commands while the parallel code is running. Otherwise, you will not get those numbers. We already discussed the metrics collected for the previous topics, but since this particular topic is important, we are going to do that again, even in a more comprehensive way. In the collected individual thread affinity, we deliberately colored the records for the worker threads red. Their lightweight process IDs, LWP, as numbers are greater than those of the other threads because, as we said before, those threads are created after the others. One can clearly detect the main thread because its process ID, PID, and LWD ID are equal. And since it is created first, its LWP ID has the smallest value in that column. Mind the load of the CPU threads. The sum of all loads detected for the worker threads must be almost equal to their number if the executed code scales well on that number of threads. Here, we show what that same metric would look like if we try to execute the same script with GIL-enabled standard Python. You may see that the CPU load per thread is very low, and the sum of those loads is close to 100%, as if only one logical CPU in the system is fully utilized by all running threads. That is something you can expect. After all, the standard Python interpreter is originally designed as a single-threaded application. We need to comment on some unusual features included in the code of the example script. In an effort to eliminate the presence of oblique pointers in the IR text generated by the Clang compiler, we implemented the re module to generate regular expressions. This step was essential because Clang 15, despite being instructed not to, integrates opaque pointers into the IR text. Consequently, even though the LLVM-like module is designed to work with Clang 15, it is unable to read the IR text. It is likely that this is a bug in Clang 15, as it is unable to prevent the addition of oblique pointers to the generated .bc files. We anticipate that this bug will be addressed in one form or another in the forthcoming iterations of LLVM Lite. Note that switching from .bc to 8L files does not solve the problem with the presence of oblique pointers in the IR text. Those pointers appear in the text even if the .l files are generated by passing 0 level of optimization to Clang 15. Given that our webinar is limited in duration, we cannot go over yet another example code. For that reason, we have added another script to the webinar repository that you can run and examine as a homework assignment. Its code is easier to understand. It executes parallel threads natively in Python and can be monitored in the same manner as the script whose execution we have previously described. And it is also supplied with developer documentation. This section is intended for more experienced Python programmers and users. By including this content in the webinar, we hope to pique your interest in native support for Python multithreading. Although this Python parallelization technique could be considered experimental, it is an impressive example of the exceptional CPython's capabilities. Proper data formatting within the Python code is critical for achieving optimal performance in multi-threaded Python applications. The choice of data structure and storage format directly impacts memory access speed. Contiguous memory layouts enable better cache utilization. Thread safety. C-style arrays can be safely shared across threads without Python's global interpreter lock, GIL. Performance. Efficient file formats like HDF5 and NetCDF enable fast data loading and saving. Computation speed. Pre-allocated arrays avoid memory allocation overhead during computation. Multi-threaded applications benefit from contiguous memory. Arrays stored in contiguous memory enable efficient cache usage and vectorization. Type consistency. Fixed-size numeric types, float64, int32, allow direct memory access without type checking. Pre-allocation. Pre-allocated arrays avoid memory allocation overhead during parallel computation. Zero-copy operations. C arrays can be shared between threads without copying. Several times in our presentation, we have spoken about C type of data and arrays. Here is a short summary why their adoption in Python code project involving multi-threading libraries helps enormously. The C arrays provide the lowest level, highest performance option. Direct C memory layout. Zero Python overhead. Can be created from C libraries or memory buffers. Maximum cache efficiency. The cover use cases as interfacing with C libraries. Maximum performance requirements. Memory mapped files. Shared memory between processes. To make up for the absence of time to present this subject in its entirety, we have prepared a comprehensive document that is replete with examples and explanations. We cannot avoid discussing how to work with Slurm to manage Python multi-threading applications, because we are speaking to an audience of HPC researchers. Do not confuse multi-threading with multiprocessing or multi-node parallelism. The critical concept to comprehend when utilizing a Slurm-controlled HPC cluster to run multi-threaded applications is that pure multi-threading is solely executed on a single node, unless it is combined with MPI to create a multiprocessing job, which execution can be performed on multiple nodes. An additional critical factor to consider is that memory is shared among multiple threads or applications on a single compute node only. In the context of the Slurm job script writing process, it is necessary to specify the use of a single node, nodes bot1, single node, and tasks per node bot1, and specify the number of worker threads assigned to CPUs per task and its relationship to threads. The example shown comprises solely the Slurm batch header portion of a job that regulates the execution of a multi-threaded job on the Discoverer petascale supercomputer, which is one of the Euro HPC CPU partitions. Here we see the way the CPU resources are allocated for running 4 worker threads. The job also reserves 1 task per node. Also, do guarantee that the number of CPU tasks managed by Slurm is assigned to the necessary environment variables that specify the number of threads available to the worker threads. Python code itself provides an additional means of evaluating the CPU resources accessible to the worker threads. It is possible because Slurm exports the parameters that describe the resources allocated for the job as environment variables. Consequently, the OS module should be employed to conduct an inquiry. To make up for the absence of time to present this subject in its entirety, we have prepared a comprehensive document that is replete with examples and explanations. And a few last words. Since the webinar is too short to cover all the topics related to the main ones, we have prepared a number of supplementary documents in the webinar repository. You should read them to gain a comprehensive understanding of using Python multi-threading. We have incorporated a comprehensive guide on the implementation of multi-threading models and libraries in Python platforms for AI and machine learning. This comprehensive Conda installation guide will assist you in utilizing Conda in the HPC way on Discoverer petascale supercomputer. We compare the agnosticness of Python threading to that of Intel 64-bit processors and their ARM64 counterparts. Next document is mostly a continuation of the previous one. It compares how hyperthreading works in real Intel processors with how simultaneous multithreading works in AMD and ARM processors. Also, you might be interested in our CPU-level multithreading analysis that discuss the multithreading application topics for TensorFlow, PyTorch, scikit-learn, and Keras. Finally, we offer a document that details the most comprehensive method for compiling your no-GIL Python interpreter, as tested on the Discoverer petascale supercomputer. Furthermore, it is important to note that all webinar materials are presented in a format that can be easily accessed by your AI agents and integrated into your daily code development, problem solving, and project development. Finally, we would like to express our gratitude to each and every participant for their time and willingness to learn something that, if it is not new to them, is presented in a way that broadens their existing knowledge.